So, hello everybody. Welcome to week 3 of this course. And what we're going to do this week is we're going to look at how you actually solve the equations of cosmic dynamics, the Friedman equation, and the other equations which we designed last week. And in doing so, therefore, we're actually going to make at least a big step towards being able to understand where the universe is going and where the universe has come from. And so we've got 3 equations which are kind of central to doing this. We've got the Friedman equation. That's perhaps the most important of those equations, and this links the rate of expansion of the universe, a dot over a, the Hubble parameter, with the density. That's the energy density epsilon, some measurement of the curvature, which is basically a statement about the total energy density of the universe. And so when we do that, if we can solve it, not necessarily trivial to solve it, but if we can solve it, then we understand how the size of the universe is going to change with cosmic time. We then have 2 other equations. We have a fluid equation, also comes from a statement basically of conservation of energy. And it's going to be very important in understanding how we solve the Friedman equation, because it links us the expansion of the universe, if you like, the a dot over the a, now not with time, but with scale factor a. So here we can use this equation, the fluid equation, to understand how the energy density E varies with scale factor a. If we understand that, then we don't have so many uncertainties in the Friedman equation, because we have E can be replaced as a function of a, and therefore we can somehow solve, i.e. integrate, or otherwise, the Friedman equation for a as a function of t. And then finally we have the acceleration equation. The universe does not just accelerate or decelerate at a constant rate, so acceleration is also relevant. That's a double dot over a and that yields us whether or not the universe is slowing down or speeding up. And we then need to couple that with an equation of state. And equations of state are potentially very complicated, but in cosmology they're very easy, because we use this parameter W, which we just call the equation of state parameter. So, quite a straightforward thing to do. And that parameter W can have a range of values depending on the thing we're interested in. So we can think about what constituents of the universe we might want to worry about. So our constituents of the universe, well, we know that the universe contains matter. It's the stuff we're made of. So it's obvious that it contains matter, and in that case, W equals 0. We can also see. The fact that we can see tells us something about light in the universe. It tells us that it must contain radiation. And that's W equals 1/3. There's a possibility that it contains something called the cosmological constant, which we'll come on to later. And in that case, W equals -1. And plausibly, it contains curvature. And so those are the things that we want to solve the Friedman equation for. And that's what we're going to do in this lecture. And another note on notation, before we go on and actually understand how these things behave. Since the universe contains multiple things, we often express this in terms of the critical density. And remember, the critical density is K equals 0. And so from the Friedman equation up here, you can just arrive at this. So it's rearranging for the critical density when this term here equals 0. You have that EC is just 3c squared h squared over 8 pi g. And so what we'll say is, for example, we'll say something like omega, capital M, matter, is just equal to the energy density in matter over the critical density, or omega R from radiation is the energy density in radiation divided by the critical density, and so forth. And so, say for lambda, of course. And so, omega total is equal to omega m plus omega r plus omega lambda is equal to some number. We don't know what that is necessarily. It's equal to 1.0 for a flat universe. We don't know that the universe is necessarily flat. And of course, I'm doing a very specific thing here. You can have more general equation of state parameters. So not just the ones that I outlined up here, but you can have other ones as well. So, you can have W equals, minus 0.5. You can have W dot, i.e. variable with time. But all of those will impact how the universe will actually evolve with cosmic time. So having set that up, we can now go about solving first the fluid equation and then the Friedman equation.